Yeah, so welcome everyone to today's security seminar. So we have the distinct pleasure of welcoming back Purdue CS analyst Dr. Anish Kundu, who is currently the head of cybersecurity research at Cisco and an IEEE fellow. So Dr. Kundu has an extensive background in our field. Right before his current role at Cisco, he served as the head of cybersecurity at Neural AI and spent several years as a research staff at IBM. So today's topic is incredibly timely for the broader computer security and privacy landscape. Dr. Kundu will be discussing quantum secure networks, addressing the immediate threats posed by quantum algorithms to modern cryptography, and exploring how we can achieve holistic, quantum-resistant security. So please join me in welcome Dr. Anish Kundu.
Thank you so much, Hansen, for the kind introduction. It's my pleasure and honor to actually go back to my alma mater um, uh, and give a talk there. It feels going back home. And thank you so much, everyone, staff, Dongyan, and of course Joel and Sean to have me over. Okay, so I'm going to talk about quantum secure networks, especially focusing on post-quantum cryptography, its adoption in real world, and how Cisco is leading that effort in the industry. So now, uh, why I'm calling it quantum security instead of just calling it PQC, I'll come back to that. And okay, so in this talk, I'm going to talk about quantum threats to cryptography and security in turn, post-quantum cryptography activities that are going on, and is PQC necessary but not sufficient? No, we'll go over that, as well as Cisco's vision of quantum resistant security. And if time permits, I'd like to give a demo or two, of the research prototypes that we have developed at Cisco Research. Uh, okay, so if you look at the landscape of quantum resistant security, which essentially is the adoption of post quantum cryptography or quantum safe cryptography. There are several aspects. One is, look at the on the leftmost corner is or leftmost side is the building blocks. Essentially, there are algorithms, protocols, artifacts that are built. Um, Essentially, there are PQC standards, NIST announced PQC standards back in 2024 August. After almost 8 years of work on announcing candidate algorithms, then finalizing some of them, and then standardizing, going through a standards process. That's FIPS 203, 204, 205. I think 206 is in the works. It should come out soon. And then across the world, there have been growing body of work. Uh, then you have also, we will also talk about briefly pre-quantum cryptography. There's pre-QC. These are the other building blocks. Some of them are not really vulnerable to quantum algorithms, or especially we'll call them as, as the common terminology is CRQC, cryptanalytically relevant quantum computer. Then there are transitional cryptography techniques, or transitional mechanisms that will help you move from pre-quantum to post-quantum, but while remaining quantum resistant. Then there are quantum cryptography, which is quantum native, or based on quantum computing, which is like QRNG and QKD, especially QKD. Um, and then hybrid cryptography. Okay, there's no specific order here I put in there, but no, so hybrid cryptography is something that actually combines one or more of these capabilities together to build a cryptography algorithm or protocol that would be quantum resistant. With that, then we move to PQC or QR compliance. If I can show a laser pointer here, yeah, this is. I talked about the building blocks here, then the PQC, PQR compliance, which is the regulatory requirements that if you, there are requirements from our federal government in United States, and then there are European Union requirements. Each space. Um, Primary geo has their own growing body of quantum resistant compliance requirements. And with that, the question comes that, how do you develop quantum resistant DevOps? Essentially, how do you develop um, systems, software, applications? How do you develop even trusted computing platforms? And then crypto agility or a static crypto agility built into that, and then we have defined at Cisco, we have defined similar to autonomous driving, or defined quantum resistant states and quantum safety levels, QSLs, from QSL 0 to QSL 5. If time permits, I'll try to go over them, but that's something I think is going to be very important on how we look into adoption of PQC. Now, then and that leads us to at the runtime, quantum safety, right, or the communication time. So we have quantum safe algorithms that are based on quantum's mathematics that is cannot be solved by CRQCs or quantum computers, known to be solved or proven to be solved. Okay, or and then in the middle, we are using them as the building blocks to build quantum resistant systems, infrastructure, or networks. And on the right side, during the runtime, operational time, uh, and communication time, how does the quantum safe states change, right? So quantum safety it depend on how you have implemented these algorithms, how you have configured them, how you are addressing different threats, and there's a crypto agility dynamic version of that is coming in. Okay, so this is the overall ecosystem, or the quantum resilience security framework that will look like. Now, we'll come to into more details, more specifics of it later, right? So, what is the overall objective of quantum security? That the question is, how can you secure quantum networks, or quantum secure networks, or systems, or infrastructure, right, and applications, right, to attain quantum resistance or quantum security against CRQCs and their specific threat models, so that they can operate. By operation we mean, right, they can operate, it's like dynamic aspect of that, how they can communicate, compute, process data, uh, or even operate and create things, right, or generate data in a quantum safe state within one environment, one network, or across networks, and across the internet and digital universe. This is what we feel is is the um, requirement of today in and how we migrate to post quantum cryptography in uh, the next few years, right? Now, the taxonomy of quantum safe quantum safety, okay, requires a more detailed look, with a more and more with a lens on it, because safety is a discrete state. Either something is safe or not safe, right? Either zero or one. Now, given the attack surface, given the uh, cipher source that are used, how they are used in a system, and the complexity of uh, even a single program, right? We cannot really guarantee whether something is safe or not at the implementation level, or at the config level or deployment level, right? And that boils down to even to maybe the halting problem. I cannot give a proof here, but I think it can be this problem can be reduced to the halting problem to demonstrate that it is undecidable to prove quantum safety of a system. And in security world, you know, we look at things in a risk specific manner, where risk is probabilistic between 0 and 1, right? um, and and that is and once you start implementing the quantum safe algorithms based on the uh, hardness assumptions of the mathematics, underlying mathematics, or mathematical problems, once you start implementing them, that is where the risks creep in, depending on the programming language, the programming environment, the configuration, how you're deploying them, blah, blah, as I mentioned, right? So therefore, it becomes more probabilistic. So therefore, we should not call it quantum safe implementation or something anymore. It is, we should call it either quantum resistant, and once we deploy that quantum resistant artifact, and use them in different contexts with dependencies among them, right? That is when we have the security risks that come in, and we call it as quantum security. So that's why the taxonomy, that the simplified taxonomy, there's a more details into it, but the simplified taxonomy that should be um, used is, you talk about quantum safe algorithms, then you talk, then the implementation and deployment and blah blah, everything becomes your quantum resilience and then quantum security. Then when you are operating at the operation level, you can call that whether a given state of a system is quantum safe or not, whether during runtime, or whether a given communication uh, at the communication time is quantum safe or not, right? So uh, please feel free to interrupt me. We can. I'm sorry, I spent good amount of time there, but so let's give an overview. I talked about a lot now, but the quantum security timeline, right? 1980s quantum computing proposals came in. 84 BB84 algorithm was published. QCAD even before Shor's algorithm was there to factorize and that we can say that RSA and public key cryptography based on factorization can be broken. That was in 1994 after QCAD was published, and in around um, 2010, right, PQ series begins with the OQS project in 2016. 2024, August 13th, NIST published the three PQC standards, and it's ongoing. And then by 2030, RSA, CDSA, or the public key cryptography will be deprecated and disallowed by 2035. That's the current timeline. But with latest advancements, just within last couple of months, okay, um, or maybe 1 month, that might change. This timeline, 2030, might come much earlier than we think. There are in people who disagree with that, and that's a good thing. That should be healthy disagreements. But we'll come to what are the new results. Try to see. Okay, so the threats, quantum computing threats for classical crypto is like you have RSA, public key cryptography, you have symmetric cryptography like AES 128 bits, right? And hashing and other cryptography primitives. They they are against Shor's algorithm that can carry out factorization. Their probability, majority of public key cryptography algorithms are going to be broken if Shor's algorithm, which is a quantum algorithm, can be implemented by a CRQC. Right? That requires 1 million plus qubits, which was 20 million, almost 20 million noisy qubits back in 5 years back. But there's a work last year from Gidney at Google who talked about that it needs 1 million qubits, not 20 million anymore. So that's a factor of 20 speed up. Now that there is, I'll come to that. I don't want to fast forward here. And Grover's algorithm, which is a tight bound on it's a quantum search algorithm, and you can that leads to reduction of the security parameter by half. Okay. So AES 128 bit would be theoretically about 64 bit, but there are, as you know, in algorithm are constants, and there are implementation costs, runtime, memory, and other costs. There are quantum error correction, decoherence, other aspects that come in, and therefore it will not be 64-bit, but it could be around 80 bits. There are some papers around that, or maybe 90 bits. Okay. However, these two algorithms have pose the threat that RSA will be broken, Diffie-Hellman will be broken, and AES 128 bit will be broken, and therefore there is this whole work on PQC is to migrate towards quantum safe cryptography, right? And Gartner predicts that by 2029, quantum computing will be able to build a CRQC to weaken existing crypto. Okay. In February this year, okay, there's a paper that came out by uh, by Jesse Van Grinsven, Victor Oliveira Santos, and Bahram Gharabaghi on a faster factorization technique, quantum algorithm that can do faster factorization than Shor's algorithm. Okay, that's a very interesting paper to read, and what it says that it can take about 5,000 qubits, which is like from 1 million to 5,000 is a significant speed up, right? And that means if the claims in the paper um, are proven to be correct, um, uh, then we are looking at a CRQC much earlier than 2030, much earlier, and therefore we need to move faster. Okay. Even before that, there's an imminent threat. Okay. The imminent threat is harvest now, decrypt later. Okay. What happens is you have data. Okay. And there are different shelf lives of different data objects. Right? You have your library card data, which may not be that sensitive. So the shelf life of that may be maybe few weeks, or it doesn't matter maybe. Then that or in some cases it might matter depending on the context of their use. Okay. Um, so um, in case of healthcare or in case of finance or defense data, right? They are subject to long-term retention due to compliance requirements. Okay. And their sensitivity value stays long, sometimes more than 10 years to 20 years, 25 years, even 50 years, and your declassification timeline for federal government data would give you a good rule of thumb of the value of the shelf life of that data. Sometimes they're also redacted after decades of remaining classified. So, if an attacker can tap onto a communication channel and harvest or copy the ciphertext of that data, okay, uh, then it can hold it, and it can later on it can use it to determine no, break it the ciphertext and determine the plain text by using a CRQC as soon as it is available, right? Of course, nobody, I believe that, no, nobody will inform the public like ChatGPT day, right? There's a CRQC for you, okay? That might happen much earlier, even the public, before the public knows, because of the sensitivity and risk it poses. Now, I didn't mention one other type of data, your cryptocurrency, right? Your Bitcoin, your ethers, and other cryptocurrency is under heavy threat due to that, because they have a longer shelf life unless that specific cryptocurrency network goes out of business. Okay, so okay. Now, how do you address this imminent threat? Right? That is where what we are proposing at Cisco is a concept of transitional mechanism, transitional remediation. Okay, I'll go into that a little later, but so PQC standardization is there. There are building blocks and quantum subcryptography is there. PQC is there. Is it sufficient? It is necessary. That's true. Okay, but is it sufficient? And I I think, and we think at Cisco, is that no, it's not sufficient. And I think the industry is slowly also coming up to understand that. Because first of all, you know, um, the mathematical hardness assumptions of the existing lattice-based cryptography are not yet proven to be quantum safe. Okay, it is believed to be. Okay, and there could be some result already. I might have missed that in last couple of weeks or so. But no, please read it if you know such proof. So therefore, it can be broken. If maybe there will be algorithms to demonstrate that lattice-based cryptography can be broken. With quantum computers, with a CRQC, with enough computing power, then the implementation of this cryptography algorithm, as you know, is not easy. And if you start implementing them correctly, even if the underlying mathematics is correct, right, then you'll bring in new attack surfaces, new vulnerabilities. Therefore, it has to be validated, and it has to be tested. That takes time. And then there are third-party cryptography validation labs niched at certain such mechanisms, such processes as well. Right? Then there are country-specific requirements. Some countries like NIST PQC standards. Some countries say, now we will have our own standards. Some say, we are going to use hybrid cryptography. Then there are export control requirements. There are crypto agility requirements, right? Now, given all these things, PQC standardization is not the hammer, or is not sufficient. It can be necessary. It is necessary in most cases, but not sufficient. Okay. Um, okay. Now, quantum threshold classical cryptography, we've gone through this. I'm not going to into this, especially this one is have communication. All of them are under threat, right? Communication, data, systems, and computation. Talked about them. The attack surface is large. We know that now. So let's do a deep dive into the threats. There are three types of threats. There are CRQC threats, right? It can break public key crypto using source algorithm, or the recent algorithm that came up a few days back. And Grover's algorithm can weaken the cryptography algorithm, the security parameter, right? And then there are imminent threats, HNDL, right? So there could be data in motion in public network that are vulnerable. Then data at rest is vulnerable. If somebody gets access to the encrypted data stored in storage or file systems, then data in use in memory, computational computing systems, TEs, and the secure enclaves, right? And then also the secure boot, all of that, right? Now, that would result in as having an HNDL, and then CRQC can take the ciphertexts and then generate the plain text data. Now, there are other types of attacks that we have defined called route redirection attacks. Sometimes there would be quantum safe communication channel in place. However, because the way routing works, routes can be redirected um, uh, um, easier than it seems to be hard, right? And then to quantum unsafe paths and hops, and where an attacker then harvests the ciphertext, right? There could be also version downgrade attacks that we don't know, right? So that the parties are forced to use a quantum unsafe cipher suits, then quantum safe cipher suits, even if they are present, right? So, and there could be different classical security attacks, and like compromise of config code, etc. And the new. These are not new, essentially. These are already there. How they can be used to address the or increase the attack surface. Right? So, um, even if is HNDL feasible even after PQC adoption, as we saw, yes, right? And sometimes the cryptography can be implemented in a vulnerable manner. There is a paper back in last year in Auckland on how the PQC standards, their implementation was broken to extract private keys, especially because the learning with error needs to be redesigned appropriately. I think NIST has already addressed that, and that was a work that Cisco Research has funded with Surgiatech. Okay, we were not involved in that, but um, there's a great work. So, so that is where comes the transitional quantum theory between HNDL now and the PQC adoption, right? And we call it trustworthy PQC adoption. Whether even if you have adopted PQC, if you have implemented PQC, is it trustworthy? Okay, there is a transitional nature of these threats, and therefore the reasons for transitional quantum threat is that PQC adoption is still going on. It is going to take time, or your PQC adoption is found to be, or the implementation, the libraries, or the configuration, or the way it is the system is running, the context, the environment, right? Or the network is working, it is broken, it is compromised, right? Okay? So you have to move from that untrusted state to a trusted state through patching or remediation, or other defense in depth um, measures for quantum safe states, right? And that transition is going to take time. There's a transitional threat, and until PQC is adopted everywhere, right? So for internet to be quantum safe, right, and almost everywhere you need to have PQC adopted in a trustworthy manner. Otherwise, just having my system quantum resistant doesn't mean that it's going to communicate with other systems in a quantum safe manner. Right? So, and this is where we have proposed the concept of transitional quantum threats and how it should be remediated. Okay. Um, Now, I'm going to skip this given the interest of time. I know only maybe what 15-20 minutes remaining. Right. Please, Hansen, please let me know when I have few minutes remaining so that I can move faster.
Yes, fine. I guess it's have around 15 to 20 minutes. Yeah.
Okay. Thank you so much. Yeah. Okay. So the quantum resistance is needed since yesterday, not today or even tomorrow. Right? It's going to take time, and as we and right now, there are several primitives that require attention as well. There are several PQC gaps like distributed ledgers, blockchains, PIR, private side intersection. There are claims that some of the homomorphic encryption schemes are actually quantum resistant, but there could be elements there, and then there are ring signatures, searchable encryption, uh, homomorphic signatures, reductible signatures, and sanitizable signatures. All of them are MPC might require attention, how to make them quantum resistant. Okay, so let's look at the next phase of how cryptography versus quantum computing is evolving. I'm going to spend a little more time. I'm not, no, yeah, you'll be saying. I think I'll have some time to go into the solution approaches in more detail, but this is important to understand this because I'm talking at Purdue and one of the premier cybersecurity institutes in the world, and at CERIAS, and therefore it's an necessary to understand that the golden era of cryptography is evolving for the next is going to evolve for the next decade or two, along with quantum computing. Okay, that's my belief, and the and that gives a great opportunity for the researchers, professors, and graduate students who want to jump into this area is going to be very important. It's necessary as well. Okay, and we see that little less. I want to bring up because whenever we had a workshop last year at SEMCCS on quantum machine security. It went really well. It was very successful. But then we see that across when I talk to in our industry as well as in academia, the interests are of course towards generative AI and everything. But here the attention is necessary because this is a as there's a CRQC that will come up soon. We need attention from academia, as well as industry. Industry is currently taking more efforts. So my ask and even request to academic community to to go beyond the uh, just the um, cryptography aspects, that okay, we want to build new cryptography protocols or PQC is already done. No, there is nothing to be done. No, there's more to be done. If you look at this quadrant, right, and therefore there should be more work, more priority given to this. So we have on the leftmost top quadrant here, pre-quantum cryptography, classical computing. No, we're in the lower quadrant. I'm sorry. Um, Classical computing and pre-quantum cryptography is here, PQC. We have seen already PQC is broken to some extent, not at the algorithm level, but at their design of the algorithms or at the implementation level, but not the mathematical hardness level. Okay, there's HNDL there. Then we're moving along this line, potentially quantum no CRQC is there yet. There are work going on how we can factorize, maybe three-digit numbers, etc. Then there are gaps in PQC, and transition to PQC is already ongoing. And we should be here on the right top quadrant, right, where CRQC may be available, and the coexistence of pre-quantum crypto, post-quantum crypto, quantum crypto, and hybrid cryptography, all of them would be there in a given system across different systems, environments, etc. Right? So then the transition will still continue to PQC and hybrid cryptography, and at that the new novel attacks will come in. This is what we are seeing already, as I saw, right? The recent paper that claims to be faster than Shor's algorithm as a quantum algorithm to factorize, um, that is already there, right? So and in this quadrant, this is the time now we will continue to see that PQC implementations, or maybe their hardness, will be continued to be questioned, um, or threatened. So on the y-axis, the evolution of computing continues to quantum computing, and the x-axis, the evolution of cryptography. We don't want to be in the leftmost left top quadrant here. We may be here on the right lower quadrant where no CRQC is available, but we have the PQC transition is happening, etc. That's a good thing. But at some point in next 4 or 5 years time frame, perhaps we'll move into the rightmost quadrant, and then we continue work to continue there. Okay. All right. Now, there are several government, I'll move on to government initiatives, recommendations, standards. There are new niche PQC standards. I'll not go into that. We can discuss that offline to how they work, their details, etc. And you can read them offline. There are a lot of work going on across different geographies across the world. USA is of course taking primary lead. China is taking a lot of lead, but that not too much is available around that. EU, especially their ENISA report is there, and their Euro Commission has recommendations about. Also, they have a quantum safe hybrid key exchanges. They're talking about UK, Australia are primary players. India is doing some, but more to be seen yet. And then in the organizational level, Cisco is leading the efforts. Then Cloudflare, IBM, was my prime uh, my alma mater between Purdue and Cisco, right? IBM Research, they are doing amazing work. And Google, of course, Google Signal, the Signal protocol, there's a quantum resistance aspect that is, I think, that has been announced. Amazon is doing excellent work. I think that has we have uh, seen some papers there as well as some blog posts. Apple, your iMessage on your iPhone says is uses PQ3, is a hybrid cryptography, and is claimed to be quantum resistant. Samsung is building hardware PQC locks, etc. So, okay, this gives a summary of that. Let me move on to the Cisco vision of quantum resistant security. Okay, that um, um, one is PQC observability or crypto observability. Here, when I refer to crypto, is not cryptocurrency, it's cryptography. Okay, so and because and PQC observability is when we want to do a assessment of the given system, artifact, or network or application, or what kind of cryptography art, protocols, algorithms are using, how they're using, where they're using, when they're using, their dependencies among them, and how we want to um, create a supply chain, and that can be represented as a CBOM, cryptography bill of materials. Back in 2022, we developed this concept of cryptography dependency graphs and supply chain. I hope I can give a demo of that left time. Then next 2 to 3 years, quantum resistance via secure middle boxes, which is mostly your some PQC deployments would be there, but then there'll be also kind of a transitional remediation process, and then in greater than 4 years, there'll be next generation quantum resistant protocols using multipathing. We have developed a multipath based key exchange mechanism that hope to talk about. Okay, so we talked about taxonomy. The holistic quantum secure network that we are talking about is given a network or an infrastructure that hosts a network and assets and data. We want to carry out cryptography observability. Okay, by observability here, it doesn't mean only runtime or communication time, it is static time. We want to be able to observe what assets are there and what are their quantum risks, vulnerabilities, quantum risks. Then based on that, how we can prioritize and plan which cryptography assets to be migrated to, so that the system or the network under concern becomes quantum resilient. and that is using the building blocks. But then currently all the implementation that is happening with pre-quantum or post-quantum are quite kind of rigid, into a system, right? But what is necessary because of the cryptography evolution landscape, as I mentioned, right, short, right? Cryptography agility is going to be important. How can you make it flexible so that during static time, config time, or runtime, it should be easier to select, or have a list of options what cryptography artifacts you want to use, and then select from them based on the risks or quantum threats, okay, or vulnerabilities in other algorithms or artifacts that you see. So, and once we have implemented that, that would provide us a holistic nature of operational quantum safety. Okay. Without crypto agility, can we achieve quantum safety? Yes, to some extent. But I think at the dynamic level, with the given threats that are coming in, and the fact that existing PQC hardness is not provable, or is not probably secure. Um, Therefore, we need to have crypto agility as a concern, and then we'll propose a quantum security governance across in an end-to-end manner. This is the framework that we are proposing, and that's our vision. That is how it is going to evolve over time. And it's going to be interoperable with classical security ecosystem. They are not independent. You know. Uh, okay, we talked about this earlier, and let me see, I have only 5 minutes. So cryptography observability, has three or four different phases, right? One is discovery. First, given a system, right? You determine, or given a network, how can you determine from its devices, from its implementation, configuration, or whatever is available to you, documentation, right? What is implemented? What cryptography artifacts are implemented? What algorithms, protocols, right? How they are configured. You take a cryptography architecture of a given environment, like Java cryptography architecture, right? Or how you have configured a given applications cryptography uh, protocols, or security parameters, etc. Right? How they are used, and are they being offered? Is this system that implements these crypto artifacts is offering cryptography services? Right? That would, of course, TPM, structured platform modules, or even HSMs, hardware security modules, would also come in that. Now, and also cryptocurrency offers verifiable randoms, right, as a service that also comes in as one of those offering services. Now, inventory, right? Then once you determine all these artifacts, then you create an inventory, right? And that cryptography inventory will have the artifacts, what they are, in what form they are. Are they in source code? Are they in config? Are binaries, or or dynamic linked binaries, or statical linked binaries, etc. Modules, where they are, how they appear, and what time points in the runtime or communication time they are used, or are accessible by internal, external programming entities, or even users. And based on that, we go and develop cryptography software supply chain graphs. It's not a tree, it's not a directed acyclic graph. It is a general graph with potential to have cycles. Okay. We can take that offline. How supply chain can have cycles? There could be. The probability is very low, but yes, there could be. Okay. Callback functions, okay, could be there. Then cryptography dependency graphs. Cryptography dependency graphs are much more granular and hold more precise information than your supply chain graphs. Okay, and that could also, the dependency graphs will also have an overlap with call graphs, right? Currently, the industry is focusing on CBOM, cryptography bill of materials, to represent supply chain graphs, and primarily these bill of materials, SBOM, CBOM, they represent at the higher granular level of files. Okay, you take a GitHub repo or something, it gives files, and then see this file is depend on that one, and or this package is imported from there, and blah blah, right? But it goes into where you make function calls, etc. And that is an undecidable problem, especially for C, C++, and other such languages where you have references and pointers, right? So this is a challenging problem. Each of these phases is challenging, as you have seen in our practice or implementation. Uh, but especially determining the dependency graphs and supply chain graph is not that easy, but we have to have phased approach to that. It will not be here. Then you have quantum vulnerability, like crypto vulnerability to Shor's algorithm, Robert's algorithm, HNDL, and of course the newer algorithms, right? So what it outputs, this whole crypto observability engine, is you have CBOM, crypto dependency graph, risks, quantum risks, and prioritize. How do you prioritize? And this prioritization sits between risks and prioritization. They sit, and quantum risk analysis, they all sit between the crypto observability and resiliency, because observability may decide this is high risk, this should be prioritized, but then in practice, if you have already worked in security teams in industry, right? You'll see that that will change the when you go to the how you remediate them. Okay, your options of remediation. Now we are also proposing one more thing here for the community, right? That um, CBOM is, or this whole supply chain dependency information, the inventories are not just going to be just one single output entity. Okay, it's going to be a kind of a matrix. Okay, in the matrix, there are, on the rows, there will be the type of the level of information, the depth and breadth of information you provide to carry out this crypto observability. Either is white box, you provide as much as information as you can. Like for example, being in Cisco, if I am a Cisco business unit, I will have access to all the source code, all the binaries, and therefore I'll be able to, and their documentation, their configuration, etc. Right? That will lie in a white box, and sometimes I may not have a source code. I have a white box without source code, right? And then there is gray box um, mechanism where we don't have access to all of them, but we have observability information with respect to how, like eBPF, and their performance metrics, their documentation, etc. Right? Then on the row, there will be also black box where we don't have any information about the running system, the running processes. Okay, can I know if this runtime system or runtime process, that server, is actually using any pre-quantum cryptography or post-quantum cryptography, right? What is it exactly? Can I go into that? That is necessary to build this, do this cryptography observability and determine the risks, right? If I cannot do that, then I have systems which are left maybe vulnerable to quantum threats, right? So we have built different research prototypes across them, and I have not named some of them we have internally, and then there is on the column. I'm not showing the column here, but there is static time. There is static time. There is deployment and config time. There is run time, and there is a communication time. So this is a basically 4 by 4 or 3 by 4 matrix where each cell represents a specific type of observability information and quantum risk and prioritization. Okay. That is something uh, we're doing at Cisco. Okay. Now, with the one of the first systems that we have already open source called Quartz Quantum Risk and Threat Analyzer. This is the architecture of that. I don't think I have time to go through that. Let me, the architecture, this is open sourced. This is the dashboard of that. And then we have a small Aqua based on Quartz that uses only net flow data and is gray box based. observability based. It can then determine whether a given communication at real time is quantum safe or not. Here we can use the term quantum safe because we're doing communication at real time. Now, I'm going to move to the other work that we have done is PQCML. We have four black box based crypto observability. We have curated the data sets and we have trained ML models. This is a work in conjunction with Northeastern University. Christina Nitarotaro, who was a professor at Purdue CS and CERIAS, and is now at Northeastern, is our collaborator, and his graduate student, Chushini Malik. So we worked on this, developing, training this ML models. These are lightweight ML models. Then it does, and the accuracy is very high. Given performance metrics, CPU and memory usage of a per process basis, we can provide, given that process, is that process using classical or PQC? If it is using PQC, then is it using what algorithm is it using? What specific library is it using? And is it using PQC or hybrid cryptography? Okay. And what protocols is it using? Okay. So this is the paper is already there, and some of the other works on are will be out at some the observability and the framework. Those pieces of work are these papers will be out in archive. And if you need an links to them, please let me know. Yeah, I'll be happy to share when they're available. Okay. Now, crypto resiliency, right? Crypto resiliency, again, I don't have much time to go into that, develop building blocks, So we have a system called multipath quantum resistance. Now, here I'd like to mention something that we have developed a working group for some time now, since last year, across different academic experts and universities. Purdue CERIAS is, of course, among them, with Professor Elisa Battino is chairing that working group, and Krishnani Tarotaro from Northeastern, Attila Yabuz from University of uh, Florida, and then Jaideep Vaidya from Rutgers. They are our collaborators and in the working group, and we're so proud to have them on the working group that are working on helping us define some of the crypto resilience frameworks and the best practices. Okay. I'm not going to multipath quantum resistance that much, but the key idea in the multipath quantum resistance is that you like multi-factor, right? Either with a single factor, single device, you provide your credentials and log on to a system, another remote system or another local system, right? There's one factor, and therefore if that factor is compromised, then your credentials will be, or identity will be compromised, right? However, if you have multi-factor, that's why multi-factor authentication MFA has become so popular and so practically useful, is that it reduce the risk, it increase the hardness for the attackers, saying that okay, if I have multiple factors, my phone, my laptop, or maybe I have another device like I think Google Titan or the RSA keys, key fobs, they therefore you need to have access to all of them or some of them to provide that kind of a mechanism. And we developed a multi-path um, assurance, or quantum assurance is what we developed. And uh, I'll not go into that much. I know. Okay. um, the last slide on crypto agility. On crypto agility, the question is, can we make a system or software flexible to recurrently and refactor crypto assets? So we defined the concept of software defined crypto agility. This is, we are given a system, given a software that is already out there, okay, or you are designing a new one, right? Can we refactor it dynamically uh, using different capabilities, including copilots? We have developed copilots, and we call CBOM copilot and crypto agility copilot. That takes this code and then creates a cryptographic control plane where multiple crypto artifacts as options or configs or policies that will hold that. And then the crypto artifact usage plan will be carried out in the business layer and the data plane, right? So the control plane implements binding during static time or dynamic time. Okay. The software code refactors, then crypto deossification is carried out, and crypto SLE code is okay. Um, I think uh, I should have spent more time on each of these details, but maybe for next time. Okay. Um, okay. Let me stop here. I don't think I can give any demos. I want a couple. If there are any questions, please let me know.
Yeah,
Feel free
thanks
to
for
ask.
the nice talk. Yeah. Let me first read like two quick questions, and one is from Aniket. So Aniket asked, so how are TE or trusted hardware vulnerable to harvest now and decrypt later attacks?
Okay, that's a great question, Aniket. And um, the trusted execution environments or hardware trusted environments, what they do essentially they provide they use public key cryptography. Okay, provide attestation or some form of authentication during runtime, and then perhaps they will be also using symmetric cryptography. Right now, even if they are not using symmetric cryptography, during the time of authentication, they can then be used to actually, for example, they are used for encrypting data so that this data can be stored in a storage sensitive data. You don't want to encrypt that during in not so trusted hardware platforms, right? So that encryption then becomes vulnerable. That ciphertext that is created by these TEs that can be vulnerable. Now, during the operation, the memory is encrypted, right? If you move to the processing time, the uh, the memory is encrypted, okay, and that will be encrypted mostly using symmetric key encryption for efficiency, right? And any ciphertext that is there, if there's a debugger attached to those processor, that system, right, can then take a dump, memory dump, have the ciphertext, and then that can be that can be decrypted using a CRQC if the sensitivity or shelf life of the data is going to be that long. Okay. Sometimes the question arises, maybe it's not that important, right? But if you look at cryptocurrency, bitcoins, right, or you look at other sensitive data, defense or finance data, perhaps this could be useful. Maybe some insider threat will take a memory dump, okay, and then take it away. I hope that answers the question.
Yeah, I guess also one quick question, a quick follow-up question from my side is, so I guess with quantum computation, whether from some classic, some side channel problems in classic crypto will be just solved by, because just of the nature of quantum, given like, okay, from some states cannot be cloned in quantum communication or, yeah. So what kind of, I mean, some advantages, right, for security, right,
For
can we
quantum
found
crypto,
from the
right?
quantum? Yeah, yeah.
Yes, that's true. That's true, Hansen.
Mhm, mhm.
That's correct. However, quantum crypto offers only symmetric key cryptography in a way. They don't offer, at least till now, or as far as I know, and that they don't offer any asymmetric key crypto for that is necessary for digital signatures or authenticity,
Mm,
etc. Right? And that you have to rely still on classical cryptography.
I see. Yeah. There's one more question here. So from Rahav, like with 1 million qubits, is it guaranteed that Shor or Groves algorithm can be able to break code? It will be able to do so.
Uh, Hassan, I lost you. There's some noise in the
Oh,
translation.
sorry, I guess my connection. Yeah, so I
Sorry
guess the
for that.
question is with 1 million qubits, is it guaranteed that Shor's or Groove's algorithm will be able to break the crypto codes, or there is still some fair probability?
Of course, the probability comes from the quantum decoherence and error correcting capabilities, right? That is, there will be certain assumptions because unless you really have that many and implemented it, right? As a systems person, I will say there's still some probability, okay? But
Mm.
there's a paper by Gidney from Google that appeared sometime, I think early last year or maybe late 2024, that claims with 1 million qubits it should be possible. However, forget about 1 million. There is another paper that has come in some recently, again in February, I guess. Um, I think it was from Australia. I don't have the beep in my head right now. And they claim that they can reduce it to maybe 100K, okay? 100K qubits for implementing Shor's algorithm. Okay, so this landscape is moving faster than people claim or imagine.
Yeah, cool. I guess that's all the questions we have so far. Yeah, so in that case, let's thanks Anish again, and yeah, very nice talk. Yeah, very interesting.
Thank you so much. Uh,
Thanks, Ashish.
Thank you,
Really
Mike. I
appreciate it.
hope you're doing great. Long
Oh,
time.
we're doing fine. Hope you're doing well too. It was great to see you again.
Thank you so much for having me. It's an
All
honor
right.
and privilege to go back to the alma mater again. Yeah.
Great. Well, we always love having you on. So,
Bye.
great. Thanks. Take care.
Bye.
Bye.
Great.
Yeah.